Hello Vulkan developers! Today we're going to take a look at a compute shader. This type of shader is the only programmable stage in the compute pipeline, which runs in parallel to the graphics pipeline on the GPU. In contrast to OpenGL, where the compute shader was introduced in version 4.3, in Vulkan the support for them was mandatory from day one. This is because Vulkan was designed from the ground up as a modern, low-level API for both graphics and compute. Since I already have a full tutorial on the compute shaders in OpenGL, I'm going to skip some of the theory and focus on the details of getting them up and running in Vulkan. The basic concept is the same. A shader program which is dispatched on a 6-dimensional space and can read from and write to anywhere inside the input and output resources without the limitations and constraints of the rasterizer. The first 3 dimensions make up the global workgroup. This is the total amount of work that we want to execute. Each workgroup is independent and cannot share memory with the other workgroups. The remaining 3 dimensions make up the local workgroup. This is usually a block of threads which is executed on a single compute unit. These threads can share fast on-chip memory and can synchronize using barriers. Same as in OpenGL, the parameters of the global workgroups are provided using a Vulkan API which initiates the execution of the compute shader, and the parameters of the local workgroup are part of the shader itself and can be used by the compiler to produce an optimized code for the specific use case. Before we get started, I'd like to say a big thank you to Navapix, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. Let's go over the architecture of today's demo and then we can dive into the details. We're going to execute a compute shader to generate a texture. The compute shader is copied from the website shadertoy.com. If you're not familiar, this website hosts more than 100,000 shaders. The ShaderToy infrastructure provides inputs such as the UV coordinates of the pixel, image resolution, current time, and etc. The shader itself is a sort of a fragment shader, which is executed on every pixel in the window. You can spend hours going over all the amazing effects here. If you want to run one of the shaders locally in your own OpenGL or Vulkan application, you will need to render a full screen quad in the vertex shader and the specific shader code in the fragment shader. You will also need to supply it with stuff such as the current time and sometimes an input texture. So the plan for this video is as follows. The compute shader will generate a texture using a ShaderToy algorithm, and this texture will be an input to the graphics pipeline, which will render a full screen quad and sample from the texture. To be able to dispatch work on the compute shader, we need a queue which supports compute. For example, my NVIDIA 1650 provides 5 queue families, where the first one supports graphics, compute, and transfer. The third queue family supports compute and transfer, but not graphics. In addition, I have an Intel integrated graphics on the CPU, which provides 2 queue families, and here, only the first family supports compute, in addition to graphics and transfer. In a previous tutorial, we've implemented a simple function which traverses the devices and selects the first device and the first queue family which supports the required queue flags, as well as the presentation Boolean flag. Up until this point, we used to call this function only with the graphics bit. I've added a Boolean flag called withCompute to the init function of the Vulkan core. When this flag is true, we add compute to the bit mask of the required queue flags. This means that in this case we're looking for a queue which supports both graphics and compute, and this will make our life easier because we will only need pipeline barriers to synchronize the compute pipeline and the graphics pipeline. When running compute and graphics on different queues, you have to use semaphores, which makes it more complex. For now, we will use a single queue. To dispatch stuff on the compute pipeline, we will need a single compute shader, a descriptor set layout and pipeline layout which describe the required resources and their binding points, a descriptor set with the handles of the actual resources, and a compute pipeline object. In addition, we will need to record the dispatch command into the command buffer. Some of this stuff is very similar to what we do with graphics shaders, but the pipeline handle is very different, so I decided to organize the code such that it will be easier to implement different compute shaders. I've created a class called ComputePipeline to serve as the base class for the concrete classes that exercise the compute shader. This class maintains a few private attributes: a shader handle for the compiled compute shader, a pipeline handle, a pipeline layout, a descriptor pool, and a descriptor set layout. Notice that the descriptor sets are not here. They are maintained outside of this class because you may want to employ multiple sets using the same compute pipeline object. The init function takes a reference to the Vulkan core, a handle of the descriptor pool, and the file name of the compute shader in GLSL. This means that the descriptor pool is not created by this class. It is provided as a parameter. I am now using a single descriptor pool with enough resources for the entire system. Next, we have a function to record the dispatch call into the command buffer. This function takes a descriptor set to be bound before dispatch, a command buffer handle, and the dimensions of the global workgroup. We also have a function that allocates a vector of descriptor sets. In the protected section, we have a pure virtual function which creates a descriptor set layout. This means that you cannot create an instance of this class, only of the concrete classes which derive from it. The idea here is that different shaders may need different descriptor set layouts, so each concrete class must provide its own layout creation function. This function is called from the init function. So the base class calls upon the derived class to provide the descriptor set layout. Next, we create the pipeline layout in the same way as we did with the graphics pipeline. Right now we assume that we have a single descriptor set layout, but we can easily expand this using a vector and support multiple layouts. Next, we create the shader module. Again, nothing new here. We used to do this in the main application class, but it makes more sense to provide a path to the shader and do this inside the class itself. Finally, we create the compute pipeline. As you can see, this is a much simpler process compared to the graphics pipeline. We have a single VK pipeline shader stage create info structure for the compute shader. Next, we call create compute pipeline. The main parameters here are the shader stage create info and the pipeline layout. We can now take a look at the function which records the command buffer. We start by binding the pipeline handle to the compute bind point. We bind the provided descriptor set handle, and we call vkcmd dispatch on the command buffer using the dimensions of the global workgroup. The last function in this class allocates the descriptor sets. This is the same as in the graphics pipeline, so you can take a closer look offline. So that's our compute pipeline base class, and for this demo, I've implemented one concrete class which derives from it, TexGenComputePipeline. As you can see, since all the common code is in the base class, we only need to implement two functions: the virtual function that creates the descriptor set layout and the non-virtual function to update the descriptor sets with the actual resources. Since every shader may have a different resource layout, the signature of this function may change from one concrete class to another. In this case, the descriptor sets are updated with the Vulkan texture used for output and the vector of the uniform buffers. The implementation of these functions is very straightforward. We have two binding points, a storage image on 0 and the uniform buffer on 1. I move the call to the vkCreateDescriptorSet function into the Vulkan core to make it easier to reuse this function. So we only need to prepare a vector of vkDescriptorSet layout bindings and call this function. We have a similar story with the updateDeskSets function, so you can review it offline. Setting the texture and uniform buffers into the descriptor sets is done in the same way as in the GraphicsPipeline. Now, to actually use this TexGenComputePipeline, I've added an object of the class as a member in the main application class. We also have a vector of descriptor sets, a vector of uniform buffer objects, and the Vulkan texture for the output. The texture is created with the usage flag bits sampled and storage. This allows the compute shader to write to it and the fragment shader to sample from it. The format is RGBA UNorm. We initialize the ComputePipeline object, create the uniform buffers for it, allocate the descriptor sets and update them using the texture and uniform buffers. Next up is the function recordCommandBuffersInternal, where we go over all the command buffers. Remember that we have one command buffer per swap chain image. We begin the command buffer as usual and call the ComputePipeline function recordCommandBuffer. However, we need to make sure that the GraphicsPipeline stuff is executed only after the compute shader has completed. For that, we need a pipeline barrier. This barrier provides the synchronization and also transitions the image from the compute shader layout, which is general, to shader read-only optimal. The source stage is the compute shader, and the destination stage is the fragment shader. But now we also need a pipeline barrier before the compute shader to transition the layout from shader read-only optimal back to general for the compute shader in the next frame. The source and destination stages are simply reversed. To execute the FullScreenQuad vertex shader and the fragment shader which samples from the computed texture, I decided to create a similar hierarchy of classes as the ComputePipeline. This is because the GraphicsPipeline classes, which we've been using so far, is kind of tailored for rendering models, and I wanted something more general. So I created a base class for all the graphics stuff called GraphicsPipeline, which is parallel to the ComputePipeline class. You should be familiar with all the Vulkan code in this class, so I'm going to skip it. From this class, we derive the concrete class FullScreenQuadPipeline. This class uses the texture from the compute shader as an input. The recordCommandBuffer function calls vkCMDDraw for 3 vertices. The vertices are defined in the vertex shader in a clever way which makes them overlap the entire window. This is supposed to be more efficient than rendering 2 triangles that make up a full screen quad. The vertex shader generates the texture coordinates from 0, 0 to 1, 1, and the fragment shader simply samples from the ComputePipeline texture. Finally, I'd like to take a quick look at the compute shader. The shader toy algorithm is pretty complex, so I'm not going to go into it. I pretty much copy-pasted it into the shader. In addition, I've added the GLSL version, the definition of the layout in terms of the local workgroup size, the output texture, which is defined as write-only, and the uniform data, which provides the current time from the application side. This time parameter is copied into the original iTime variable, and this allows the shader toy code to execute without any modifications. At the end of the shader, we have a main function which executes the original main image function over a 3x3 kernel, accumulates the results and stores the average into the output texture. The global invocation ID parameter provides the address of the output pixel. So that was quite a lot of code to cover, but if you look closely you can see that most of the compute shader stuff is in the new ComputePipeline class, and even there a lot of stuff is the same as in the GraphicsPipeline. So I think that most of the challenge today was in organizing the code in classes to make it easier to see the general structure and not get lost in all the small details. Thank you very much for watching, and I will see you next time.